Alrighty, so this is part 2. We're still looking at polynomials and how we can find ways to find solutions of polynomials, different ways to analyze the actual equation of a polynomial. So we talked about synthetic division and long division yesterday, or in part 1, as a method to being able to check to see if something is factorable and to break things down. Those are great strategies that we're going to continue to use today, using something called the remainder theorem and the factor theorem. So these are two theorems that we're going to use to help us determine whether or not a binomial is a factor of a polynomial, which in turn will help us figure out, hey, what are the solutions of the zeros of that polynomial? Because sometimes it's not always very easy to factor things, and it's nice to have some other options to be able to do that. So I'm going to bring you back to our last example from part 1. So we did synthetic division. Remember, we put in placeholders for the terms that we didn't have any representation for, to make sure we had terms to subtract from. And we found that this one had a remainder of 1372, meaning it didn't divide evenly by x minus 5, but we could nonetheless still do the division. So I'm going to come to the first theorem of the day, the remainder theorem. So it has something to do with the remainder of a polynomial when you divide. And it says that if a polynomial, f of x we'll call that, is divided by a binomial linear factor. Okay, linear means degree 1, binomial 2 terms, so like x minus k. K is just standing for a number, like k for constant. Then the remainder, so we're going to call that r, just like the little r used in elementary school, is equal to f of k. What does f of k mean? It means the value of the function f evaluated at k. So like plugging the number k into the equation and getting your answer should be the same as whatever remainder you get when you divide it by the binomial x minus k. That can be a real time saver for us because we know we have a couple different ways then to check the remainder. So how do we use the remainder theorem to help evaluate a polynomial? Well, if you divide f of x by x minus k, either long or synthetically, the remainder will always be the exact same answer as just plugging the k value in. So I want to illustrate that with the example that we did from yesterday. So yesterday we did the synthetic, right? So that's the dividing it. We just chose to do synthetically. We could have also done long division. What I want to show is that's actually the same value as just substituting in, this is like our k value here, the 5 into the function f, and it'll be equal to the remainder. So it's saying the remainder is going to be the same as the value of the function. So let's double check. Here's what I'd like you to do. I want you to replace all your x's with 5, and I want you to pause the video, and I want you to do the arithmetic. Now you can do it in your calculator, that's totally fine, but I want you to find the value of this function at 5. So go ahead and pause the video and do that calculation. What I'm hoping that you're going to see is that you get that 1372. So what does that mean? Let's go back to our synthetic division. The 1372 was the remainder when we divided synthetically. It also happens to be the exact same value as when we substitute in the 5 into the function. So the remainder is equal to f of 5, which was equal to the 1372. Okay, so why do I care about that? We're going to talk about that when it comes to being able to find if something is a zero or a factor of a polynomial. So it's going to be really helpful. But let's practice that first, just to be sure you know you always have two options then to be able to determine the remainder when you're dividing. So it says use the remainder theorem to find each value given. So let's just start with this letter a, f of -1. So we all know one way that we could find f of -1, right? We could just substitute that value in for x and we can solve, right? So we can do that arithmetic and see what we come up with. So go ahead, pause the video, see what you get. So I want you just to do your regular plug and chug, as we call it, plug it in and chug it through, see what you get for that value. All right, so hopefully you were getting the value -1 when you did that. What does that mean? That means if we put in the value -1, I believe, oh, +1, sorry. I'm using the wrong sign here, so it should have been +1. If we plug in the value -1, our output, or f of -1, was 1. So the ordered pair that's associated with this location would be -1, 1. What the remainder theorem says is that if I divide this in either long division or synthetically, and for me synthetically would be easier, the remainder that we get when we divide synthetically should be exactly the same as just plugging the number in. So let's double check. So if I'm dividing by -1, let's go through and do that synthetic division again. Bring down the 4, multiply, we get -4. And remember what we do here with those two numbers? Remember, it's bad. That would be 6, and then we multiply, we get -6. So -9, we multiply here, we get +9, and we add, and we get the 1. So notice f of -1 is equal to the remainder, which is equal to 1. They're both the same. Okay, so you always have your option. You can do this either way. And again, I chose synthetic division. You could do long division if you wanted to. All right, so I want you to go ahead and do the same thing now, but try it with f of 4. Choose your method. So you can either substitute the value in and do the arithmetic, so you can plug in the 4, or you can go ahead and do synthetic division to show what that answer is for that value. So go ahead and choose your methods. You can either do this or you can go ahead and do your synthetic division. All right, so for using f of 4, I got 396, and when I did my synthetic, or if you do long, you're going to get the same value. So again, the remainder is equal to the value of the function in both of those cases. So I get the exact same number. So the ordered pair associated with this would be you substitute in a 4, you get 396 for your answer. Now remember, a quick little tech tool here. You can always use your graphing calculator to help. So I went ahead and put that equation in. I can just go to my auto-generated table, right? So I can see my 1 or my -1, 1, and my 4, 396. They're both on there. Otherwise, remember, you can always change your independent variable to ask, and then you can ask whatever values you want in your table. So I can say, hey, I wanted -1, and I wanted +4, and I can get those values really quickly. So it is a time saver if you want to use that value. Okay, so let's talk about what's the implication for this then. Why am I talking about this remainder theorem, which brings us to the factor theorem. So if you take a polynomial, so we're going to call that f of x, and you divide it by a factor. So factors mean it's something that divides into a polynomial evenly. So it has a factor then, or it divides in there evenly, if and only if the value of the function is 0, right? So remember what a factor is. Remember we went through the list of 4 different things. We can call it a 0, an x-intercept, a solution, or that linear binomial term x minus k is a factor. Those all mean the same thing if and only if f of k is 0. In other words, if you plug the number k in, you get 0 for your answer. Those are the ones that are factors. They divide in there evenly, right? So they have an even or 0 remainder. So what we can do then is we can use this idea of, hey, the remainder is 0, or if I plug the number in, it's 0, to help us find factors a little bit more quickly for our polynomials. So here are your two options, and it's exactly the two methods we just talked about. We can use the factor theorem to show that x minus k is a factor one of two ways. You can evaluate the polynomial like we always have. Hey, plug in the number and to see if f of k is 0. So we can just substitute that in. Then the x minus k is a factor. We know that it's a 0 or a solution of the function, and so the binomial term is a factor. Or you can do your division. You can divide the function f of x by x minus k. If the remainder is 0, then x minus k is a factor. Because remember, the remainder is exactly the same as the value of the function when you substitute that k in there. So it really does give you options. Now let's compare the green one and the blue one, which one might be better. The green one will tell you if that number is a factor, and it works really well. But that's all it tells you. It doesn't tell you about any of the remaining factors a polynomial might have. If you divide it synthetically or long division, depending on what you want to do, you not only can find out if a binomial itself is a factor, but then you can use the polynomial you have left over, that quotient, and you can see the remaining factors as well. So the second option is more useful if we're trying to find all the factors of a polynomial instead of just the original one that we're trying to check about. So we often will default to number 2 because it's going to tell us more information. So it's a nice way to do that, and synthetic division works pretty quickly, so we can find out what those values are. All right, so we're going to try an example of how this factor and remainder theorem can be useful in figuring out not just factors, but also then zeros and solutions of a polynomial. So let's take a look at this polynomial here, this f of x. So what degree is it? So take a peek. So it looks like we have a degree 3. So remember, the number of zeros then, the number of possible factors or zeros, either way you look at it, is 3, right? Because we have three different things multiplied together will give you something that's degree 3. So this graph could cross the x-axis up to 3 times. Our quest here by finding the factors is to be able to find those zeros. So we're going to try to see if x plus 3 is a factor. Now, normally we wouldn't just kind of randomly guess and check, hey, is this a factor? Is this a factor? You would just try to factor the original thing itself. But take a look at that trinomial. That's not something that's going to factor easily, right? We can't just break that into two binomials. There's nothing that multiplies times itself to give you an x cubed. There's no GCF. We would really be stuck. So we're going to talk about guessing and checking and what are some good ways to do this. But for the purpose of just illustrating the factor theorem and seeing how that works for us, we're going to see if we can do that to help us solve. So remember, the factor theorem says if it divides into this polynomial evenly, zero remainder, then it's a factor. So we can do that division. So let's take a look and see what that k value would be. Remember, we write these as x minus k. So if you see a plus 3, that means it's coming from minus a negative 3. So our k value that we're looking at is actually negative 3. All right, so now remember the two different ways we can check to see if something's a factor. We can do the division, and we can see if we get a zero remainder. Or we can just plug the number in and see what we get if we get 0. Now, the just seeing if something's a factor, maybe I would do it that first way. But again, remember our conversation, this second way is probably better because I want to find all the other ones as well. So I'm going to go ahead and do division to be able to solve. So I'm seeing if this is going to have a zero remainder. So let's go ahead and do our synthetic. So my degree 3 is a 1. Do you have a squared term? Think about that. Pause the video, write out the rest of your coefficients. So no square term, we need a placeholder, negative 19 and a negative 30. Okay, so we're going to check and see if we get our zero remainder. So go ahead, pause the video, do your synthetic division, see what you get. So I'm bringing down the 1 and I multiply negative 3 and add. Remember, we multiply, we get 9 and add, and we multiply, we get positive 30, and there's what we were looking for, zero remainder. What that means is f of negative 3, if I would have just plugged in negative 3, I also would have gotten 0, and you can double check that when you put that in there. So what does that mean? You got a zero remainder, divides evenly. That means x plus 3 is a factor of this polynomial. It divides into it evenly. Okay, so think about what you have left now. When we did this division, this x cubed minus 19x minus 30, we divided it by x plus 3. What did we get for our answer? Well, that's what they call the depressed polynomial is. These coefficients are going to give you that quotient, that value. So remember, we go from the remainder. So this was our remainder. We know that that was a 0. This is your constant then. This is your degree 1. And this would be your degree 2. And that kind of makes sense. A degree 3 divided by a degree 1 should be a degree 2. So these are the coefficients. So this is x squared minus 3x minus 10. So another way to say that then, if you want to think about this, that's your quotient. That means this x cubed minus 19x minus 30 is really equivalent to the x plus 3 times the x squared minus 3x minus 10. Right, because if I multiply those two together, do the distributive property and all of that, I will get back to this original polynomial. Multiply both sides here by that x plus 3. That's the opposite operation of division, right? Multiplication. So I have shown that, yep, this first one's a factor because I got a zero remainder. Now I can take this polynomial that I have left, this x squared minus 3x minus 10, and factor it further. So if it's factorable, I'm going to be able to find what they call the remaining factors. So let's see if it's factorable. Remember, not every degree 2 is. We could use quadratic formula if we weren't sure, but this would be x times x. What multiplies to a negative 10 and adds to a negative 3? So pause the video, write in your factors. So that would be minus 5 and then plus 2. So the remaining factors are x minus 5 and x plus 2. So this x cubed minus 19x minus 30 are equal to those three factors. So now here's the super cool thing. Once you know the factors, the things that you multiply together, we can also then find the zeros or the solutions. So the zeros are setting each of these equal to 0 and solving. So we'd have an x equals negative 3, an x equals 5, and an x equals negative 2. That means we know where this graph crosses the x-axis, right? We can see where those locations are. So negative 3, negative 2, and 5. We know it's degree 3, so we know what the end behavior is. These are all happening with a multiplicity of 1. So a multiplicity of 1, meaning odd, meaning it's crossing the x-axis at each of these values. We know what our y-intercept is because we have our constant, so somewhere way down here at -30, and we can actually get a really good approximation of what this graph is going to do. So we know our end behavior is going to fall to the left because it's degree 3 and our leading coefficient is positive. It's going to cross, it's going to cross, and it's going to cross, and it's going to rise to the right. I can get a really good sketch because I know what those zeros are. Now, let's go back up to the original question then. So did I find my remaining factors? Absolutely. I actually did more than that. So the green here is my factors, but that's what we're going to do with it, right? That's what we're going to be able to deal with because we can check to see if something's a 0 really quickly. All right, so let's take a peek, and I'm going to ask it the other way now. So I'm going to say, the last one I asked for factors. Now I'm going to say, show that x equals -3 is a solution to the polynomial, and then list all the real solutions. So kind of going as far as what I did in the last one. By saying is x equals -3 a solution is the same thing as saying is x minus a -3 or x plus 3 a factor. That's basically the same question I was just asking, different polynomial, but now I'm asking it just from the 0 perspective. So again, how do you show that something's a solution? That means you'd have to do f of -3 and see if you get 0, or you can divide the polynomial by x plus 3. So we have those two options. Now again, if all I was going to do is just, hey, I just want to see if that one thing is a solution, I could just plug the number in. But I want to find all the real solutions. I want to find the other ones as well. So division's a better way to go. So we're going to go ahead and do our synthetic division. And again, go ahead, pause the video, take a look at your polynomial. This is your f of x. Go ahead and do your synthetic division, write out those, and see what you come up with. All right. So hopefully when you did your synthetic, you got that value. Now, if you notice, all the coefficients in this polynomial were positive, and we're dividing by something negative. If we need to make a 0, that kind of makes sense. We're going to look for some of those ideas and thoughts as we're trying to come up with these guesses ourselves. I'm kind of giving you the guesses right now to see what's a solution, but as we think about kind of trends and strategies, that's a good thing to look for. If everything's positive, we're going to need to get a negative in there to get this wonderful remainder of 0. What that means is, it means that x equals -3 is a solution. We have the value that made that function 0, which also means that x plus 3 is a factor. Remember, that's saying the same thing, just writing it in that factored form instead. All right, so I know that -3 is a solution. How do I find the other ones? We're going to use this depressed polynomial. They call that those coefficients that are left. So remember, we did our 2x cubed plus 11x squared plus 18x plus 9. We divided by x plus 3, and we get what? Okay, so can you write out what this polynomial would be with those coefficients? Go ahead, pause the video, write it out. So 2x to the second plus 5x plus 3. So we get that polynomial. Now when I take a look at what's left, so that polynomial that's left over, I can try to factor it then to find the remaining factors. So remember, this is the same thing as saying this original polynomial is equal to x plus 3 times this polynomial, 2x squared plus 5x plus 3. So we're going to try to factor and see if we can go further. And again, if you can't, you could always use quadratic formula. All right, so let's see. How do you get a 2x squared? Well, you don't have any option here. It's got to be 2x and x. The last term's a positive, so what does that tell you? Signs have to be the same. The middle term is a positive as well, so that means not only are they the same, they're both plus. Okay, what multiplies to give you a 3? There's literally only one option, 1 times 3. You just have to decide where you're going to put the 1, where are you going to put the 3? Neither of those things add to 5. That's because there's a 2 out here. You've got to decide how to make a 3. Well, or make a 5 with a 3 and a 1. So I think we want it this way. Outsides would be 2x then, and insides would be 3x, and there's your 5. So we have it factored, completely factored. Now remember, those are the factors. We want the solutions or the zeros, so we set each of those equal to 0 and we solve. So the x plus 3 equals 0, we knew that one, that's the one that they gave us. The middle 2x plus 3 equals 0 and x plus 1 equals 0 are going to give us our other two solutions. So this looks like -3 halves or -1.5 and -1. So again, these would be the solutions or the zeros they're the x-intercepts on the graph. So again, we can make a really quick sketch here. It's not going to take us too long because we know really good information about this graph. And everything's negative. So it's crossing at -3, it's crossing at -1.5, and it's also crossing at -1. The y-intercept is up here at 9. We do know what the end behavior is again because it has a positive leading coefficient. So that leading coefficient test, we know that the graph is going to do this, our end behavior. And the multiplicity of all of these is equal to 1, which is odd. And remember what that means? It crosses. There's no just touching, it's going to cross. So it's going to go up, it's going to go down, it's going to go up, and then it's going to continue to increase. It can't change. The number of turning points, since this was degree 3, our number of turning points was 2. So increasing to decreasing was 1, and decreasing to increasing is 2. So that's the maximum number. So being able to double check if something's a solution, very critical, because then we were able to tell not only was that a solution, by doing synthetic division, by choosing this method, we were able to also find the other ones by factoring that polynomial that was left over. All right, so we're going to do a little investigation, I guess, for this one. So here's a polynomial. X minus 2 is a factor of this polynomial, so I'm going to tell you that piece of information, but I am missing one of my coefficients. I don't know what that one is, that k value. I can't tell. I don't know what it is. Can't read it in the writing because, of course, sometimes I can't read kids' writing, right? So if I know that that is a factor and that's the polynomial I'm just missing, how would you figure out what k is? So I want you to pause the video, think about the different ways that we've talked about how knowing something is a factor and what that might mean, and see if you could come up with a way that would help you decide what that number k would have to be. Right, so I'm going to go back. Hopefully you went back to our conversation about the two different ways we can evaluate the polynomial at the value when it's a factor, or we can divide and see what the remainder is. I'm going to use that same conversation here. So think of it the first way. What if I know that x minus 2 is a factor? That means f of 2 would have to be equal to 0. Okay, because remember, this is your x minus k. All right, well, couldn't I substitute in then the 2? And I know that my answer is supposed to be 0, right? Because that's what it means to be a factor. And you could just solve. So I could actually go through and I could put together any terms that I need to here. And I can go ahead and solve for that variable. So I'd have 24 plus 2k equals 0 because these 8s would add to 0. We'd have -24 equals 2k. K equals -12. And I can solve really easily that would have to be a -12. That's one option, but remember and that works great. That's a pretty straightforward way to do it. But remember, the second way is if you divide and get a 0 remainder. So couldn't I do that too? Let's see if we can do the division. So I'd be dividing by 2. My coefficients would be the 1, 6, k, -8. This is kind of the fun one to do some investigating. So you could start off, okay, bring down the 1, multiply, add, multiply, and then we kind of get to a weird spot. This would be k plus 16, which doesn't super help if I keep going forward because I'm just going to get kind of a complicated deal. Let's work backwards from the end. What would this number have to be if k minus 2 is a factor? Well, the remainder has to be 0. So -8 plus what would give you 0? Well, that would have to be 8, right? So think about what values would have to make this true then to make that an 8. So 2 times what would give you 8? Well, this would have to be a 4. So what you're really saying is k plus 16 would have to be equal to 4. There's no other way to make that happen. So that means k would have to be -12. So either way, we could actually work that through. So it's kind of cool once you understand the different ways we can talk about something being a factor, and we're going to be able to solve and find those. All right, so our essential question, how can I use the remainder theorem and the factor theorem? We can substitute in the value or we can divide. Ultimately, we're looking for the value that gives us a 0, either for the remainder or the value of the function to tell us it's a factor. If it's a factor, we know it's a 0. And then even better, when we use that division, we can find the remaining factors and zeros.